You are standing on the top deck of a cruise ship, drink in hand, watching a tropical coastline drift into view. The ship slows. The engines quiet down to a low rumble. And then, somewhere below the waterline, something happens that you never see, never hear, and never think about. The ship stops. Just stops. Sitting motionless in open water, half a mile from shore, as if it simply decided to stay there. You assume there is an anchor. Of course there is an anchor. That is what boats do. They drop an anchor and they stay put. Simple. Obvious. Done. Except that is not what is happening. Not even close. These ships weigh up to 230,000 gross tons. The largest ones are longer than the Empire State Building is tall. They carry 5,000 passengers, 2,000 crew members, restaurants, theaters, casinos, and enough food to feed a mid-sized town for a week. The idea that a lump of metal on a chain is holding all of that in place the same way a lake anchor holds a fishing boat is not just an oversimplification. It is a different category of physics entirely. The anchor is real. The chain is real. But what they are doing, and when and why and what happens when they cannot do it at all, that is a completely different story from the one most people are carrying around in their heads. Start with the chain, because the chain is where the comfortable assumption first starts to break down. When a cruise ship deploys an anchor, it is not just lowering a heavy object to the bottom. It is managing a massive mechanical system under load. Each anchor on a large cruise vessel weighs somewhere between 10 and 30 metric tons. The chain connecting it to the ship is made of individual links that can weigh over 100 pounds each. The full chain run for a single anchor, the total length deployed and stored, can stretch 300 to 500 meters. That chain alone, before the anchor is even counted, weighs more than a fleet of fully loaded semi-trucks. It lives coiled in a room below the waterline called the chain locker, a chamber so large that crew members have to physically enter it for maintenance. This is not nautical equipment in the romantic sense. It is industrial machinery. The windlass system that pays the chain out is a massive powered mechanism. Deployment is a controlled, timed operation coordinated between the bridge, the deck crew, and engine. Control: you do not drop a cruise ship anchor, you execute a procedure. When an anchor chain is deployed in shallow water, it forms a curve along the seabed before rising up to the ship. That curve, the catenary, is what actually absorbs the horizontal load when the ship tries to drift. The chain lying flat on the bottom acts as a buffer. The anchor digs in and resists the pull transmitted through that curve. That is how it works. That is what makes it effective. But as depth increases, the geometry changes completely. The chain can no longer lie along the bottom. It hangs. And when a chain is hanging in deep water, its own weight becomes the dominant engineering consideration. The ship is no longer fighting current and wind through an anchor's grip on the seabed. It is fighting against the weight and sway of a suspended column of steel. Beyond a few hundred feet, traditional anchoring does not become difficult. It becomes physically incoherent as a strategy. So where do cruise ships actually anchor? Not in the open ocean, not in the deep water, between ports. While the ship is transiting from one island to the next, the ocean floor below it might be 10,000 feet down or more. Anchoring is not attempted, not considered. The ship is moving continuously, running on propulsion and navigational routing, pointed at its next destination. The anchor is not a transit tool. It was never designed to be. The actual anchoring happens somewhere much more specific and much more interesting. It happens at tender ports, places like Grand Cayman, Santorini, Bora Bora. These are some of the most iconic destinations on any cruise itinerary. And they share a critical characteristic. The ship cannot pull up to a pier. In Grand Cayman, the harbor is too shallow for a vessel drawing 30 or 40 feet of water to dock safely. In Santorini, the caldera is deep, but the infrastructure for large ship docking is limited. In Bora Bora, the lagoon and reef system makes direct docking impractical for ships of this size. So, the ship anchors offshore and passengers are ferried to land in smaller boats called tenders. This is standard procedure. But what it means for the anchoring question is significant. The ship is not anchoring in deep water. It is anchoring in carefully surveyed, carefully selected shallow zones that look, from the passenger's perspective, like open ocean. The water around Grand Cayman's anchorage area is generally in the range of 30 to 60 feet deep. That is exactly the kind of depth where traditional anchoring works. The fact that there is no visible shoreline immediately adjacent, that the ship appears to be floating free in open water, creates the impression of deep water anchoring. But the seabed underneath is mapped, known, and pre-approved for anchorage. The ship is not improvising. It is executing a planned operation at a location that was selected months in advance. This is the first major reversal. The anchor is not a deep-water tool at all. It is a shallow water precision instrument, deployed at specific, pre-cleared coordinates in a depth window that makes the physics work. The open ocean never enters the equation, and even then, dropping the anchor is only the beginning of the operation. The ship does not anchor and go quiet. The engines keep running. Watches are maintained on the bridge around the clock. Officers monitor wind, current, tide, and the positions of other vessels sharing the anchorage. Because a ship at anchor is not stationary in the simple sense, it swings. As the wind and current shift, the ship pivots around its anchor point, tracing an arc whose radius is approximately equal to the length of chain deployed. That arc is called the swinging room, and calculating it correctly is essential. If another vessel anchors nearby, their swinging arcs cannot overlap. If there is a reef or a shoal within the swing radius, it becomes a hazard. The seabed survey that cleared the anchorage zone has to account for what is not just beneath the ship, but beneath the entire circle it might describe over the next 8 hours. Anchoring a cruise ship is an active, continuous, monitored operation. It looks like the ship has stopped working. It is not. It has shifted into a different kind of work. Now introduce the threshold where even this carefully managed system reaches its limit. Sea state, wind, swell. The Beaufort scale, the standard classification for wind speed and sea conditions, is not just a meteorological curiosity on these vessels. It is an operational trigger. When conditions exceed the thresholds the ship's master has established for safe anchor holding and safe tender operations, the whole system shuts down. Passengers get the announcement that tender operations are canceled for the day. The port is skipped or the ship repositions. What they are told is usually attributed to weather. What is actually happening is that the system has reached the edge of its designed operating envelope and responded correctly by stopping. The anchor, no matter how heavy, no matter how well the chain is deployed, cannot hold a 100,000-ton ship safely in place when wind and swell are pushing against it with enough force. The math stops working, and the ship knows it. Which brings in the second system, the one most passengers have never heard of. Dynamic positioning, DP. On certain classes of modern vessels, expedition cruise ships, some high-end luxury lines, offshore drilling platforms, scientific research ships, the anchor is either a last resort or entirely absent from the station-keeping strategy. Instead, these vessels use a system of GPS arrays, gyro compasses, wind sensors, and current sensors feeding continuous data into a central computer. That computer controls a set of azimuth thrusters, azipods, that can rotate 360 degrees and fire in any direction. The system reads the ship's position, calculates the forces acting on it, and fires the thrusters in real-time correction pulses to hold the vessel within a few meters of its target coordinates. No chain, no anchor, no seabed contact. The ship holds its position through continuous invisible calculation and thrust, correcting for wind and current in real time automatically, without the passengers feeling anything at all. This is the deeper twist. The most sophisticated form of station keeping happening on modern vessels does not use an anchor. It uses software. The system that looks most like magic, a ship sitting perfectly still in open water with nothing visible holding it, is not anchored at all. It is computing continuously. Beneath a deck where someone is ordering a poolside cocktail, the ship's positioning system is making hundreds of micro-corrections per minute, burning fuel to hold a coordinate, solving a physics problem that a chain and a lump of metal could never address. Offshore platforms use the same principle at scales that are almost harder to comprehend. Some deepwater drilling platforms hold position in water thousands of feet deep, in open ocean, in real weather for months at a time, using nothing but dynamic positioning. The anchor, as a concept, has simply been replaced by computation. The two systems together, traditional anchoring for shallow tender ports, dynamic positioning for everything the chain cannot handle. Form a complete picture of how a modern large vessel stays where it is supposed to be. They are not redundant. They are complementary. One is hardware, one is software, one has a depth limit. One does not. And the boundary between them is not a clean line. It is a set of engineering judgments, vessel specifications, regulatory requirements, and operational decisions that vary by ship class, route, and operator. Come back now to the image at the beginning. The ship sitting motionless. Coastline in the distance, water in every direction. A passenger on the upper deck with no particular reason to wonder what is happening below. What the passenger sees is stillness. The ship is just there. It looks almost lazy, natural, like a large thing at rest. What is actually underneath that stillness is either a carefully managed shallow water anchoring operation, pre-surveyed seabed, calculated chain catenary, running engines, bridge watch, tide clock, swinging room mapped to the meter, or a computer processing sensor data and firing azimuth thrusters in real time to maintain a coordinate with no physical connection to the ocean floor at all? Neither of those things is visible. Neither is audible from the pool deck. Both are completely invisible to the experience they are producing. That is not an accident. That is the design. The best infrastructure works this way. The most sophisticated engineered environments are consistently the ones that feel the most effortless from the outside. The complexity goes in so the simplicity can come out. The operational intensity produces the calm surface. The system is working hardest precisely when it appears to be doing nothing. The anchor was never the answer to the deep water question because deep water was never where the anchor was meant to go. The ship does not anchor in the open ocean. It navigates through the open ocean and anchors in specific, managed, shallow water zones selected because the physics actually work there. And when the physics stop working, when depth, weather, or sea state push past what the chain can handle, a different system takes over entirely. One that has no visible component at all. The ship holds its place in the world through a stack of decisions that were made long before it ever left port. Survey data, deployment procedures, threshold calculations, thruster geometry, satellite coordinates, none of it shows. All of it is running, and the anchor, the thing you probably pictured first, that massive industrial hook on its chain of 100-pound links, is not the answer to how a cruise ship stays put. It is just the most visible piece of a much deeper answer, which is, in retrospect, a reasonable description of how most things that look simple actually work.